Hello guys, welcome back to ptet.chemistry channel. So in this tutorial video, I'll cover this Cambridge International O-Level exam. This is a 14 to 16 years old curriculum, and it's equivalent to the Cambridge IGCSE, which is the International GCSE. So IGCSE and O-Level chemistry, they are almost identical. In fact, most of the if I'm not mistaken, all of the learning objectives are exactly the same. This is a multiple choice component. This is a paper 1 for O-Level, but I think for IGCSE they have a different paper, either 2 or 3 or something like that. But regardless, the chemistry content within will have been suitable for any 14 to 16 years old learner. This is the June 2013, a paper 1 variant 1. Even though it's a 1 hour paper, usually I would take slightly longer than 1 hour because I'm doing this by thinking out loud, and in a way I am kind of talking non-stop as well. So if you do enjoy the tutorials on my channel, so don't forget to click the button on the bottom right, subscribe to the channel. They're all entirely for free, and get connected at ptet.chemistry on Instagram, Facebook and Twitter. To simply get connected, and you can send in your queries and I can try and directly reply to you if you or I'll answer in one of these Ask Me Anything session that I still haven't gotten around to doing, but I will get around on the channel in the future. But now is exam season, and a lot of students in some countries have actually been exempted from the theory paper. It turned out that they'll be assessed entirely on these multiple choice as well as alternative to practical. It's not the case here in Brunei, where I'm based, but it is the case in other countries. So I do understand the frustration of trying to get 40 out of 40 for MCQ. Let's get trying. In this first question, we have separation technique. So we have this thing called RF. RF is short for something called retention factor. And we talk about RF in chromatography, where there is the distance moved by the solute, each of the components separated, divided by the distance moved by the solvent. So from the baseline to the solvent front is always going to be more than from the baseline to the individual solute. That is very clearly a paper chromatography kind of technique, the kind of measurement you do when you try to do paper chromatography. Question 2, the diagram shows the arrangement of particles. So we have 3 solids. By the way, these are all solids. Krypton. Krypton is a noble gas. I think the writing is too fine. Let me try this. Yep, that looks about right. Okay. When it's too fine, it's quite hard to read actually. Potassium is a group 1 metal. Sodium chloride is, well, NaCl. And we know in NaCl we have a giant ionic structure that consists of ions, okay, positive and negative, whereas metal is positive ions and electrons. By the way, electrons are not ions, okay, whereas negative ions are ions. They are called anions. Of course, noble gas exists as individual atoms because they don't form bonds with themselves, so they just exist as individual atoms without transferring or losing or gaining or sharing electrons. So I'm pretty sure that you should be able to tell this is going to be NaCl, this is going to be the metal, potassium, and that thing there is going to be the krypton, existing as individual atoms. In which order are the solids shown? So from left to right, we have sodium chloride, and then we have potassium, and then we have krypton. So this is giant ionic structure, this is giant metallic structure, this is simple, we call it simple molecular structure, even though they're existing as an atom, but some textbook or some exams, sometimes they'll give you the option of simple monoatomic structure is also equally acceptable. Question 3, in which pair do neither mean both of them do not? Okay, so negative, both of them do not. Okay, I better write it down. So both does not, do not, I don't know. I mean, my grammar is not the best in the world, so you gotta pardon me for that. So does not change the color of blue litmus paper. So blue litmus paper, blue turning to red, is a test for acidic gas. or acidic impurity or acidic substance. So we're looking for something which is acidic. So therefore, we are looking for something which is acidic. So do not change. Therefore, we look for acids, or we look for acidic gas. If you are acidic gas, you don't turn blue litmus paper to red because there's a test. Hang on, am I correct? Blue turning to red is a test for acid. You do not change the color because you are basic. Sorry, because you are basic. That makes sense. So we are looking for basic or alkaline gas. You see, it's quite frustrating sometimes when you make a mistake like this. But good thing I managed to spot it from my line of reasoning. So blue to red is a test for acidic gas. Does not change from blue to red means it's not acidic. It has to be alkaline. So ammonia is alkaline. Hydrogen is neutral, so they do not change any pH. They want neither. That means both of them do not change. So A cannot be the answer. Ammonia is basic. HCl is acidic. In fact, it can dissolve in water and it will give you hydrochloric acid. So HCl cannot be the answer there. Carbon dioxide is... Let me see. Oh, wait. Hang on. A must be the answer. You know why? I just remember. Do not change. Do not change means hydrogen is neutral. It will not change the color of that. So A is definitely the answer there. And I was reminded by it because I had a look at carbon dioxide. So I know carbon dioxide, CO2 plus H2O give you this acid. This is called carbonic acid. It is present in your carbonated drink like cola, Pepsi, or any other fizzy or carbonated drink to give you this weak acid, which will turn blue litmus paper to red when dissolved in water. So I was right. Well, I mean, I wasn't right, but you know, I kind of got the answer already before, but without realizing that even though hydrogen is neutral, and I thought it would change the color, but it didn't. As I mentioned, it's neutral. It doesn't change the color of that blue litmus paper. Question 4. We have naturally occurring bromine. The relative atomic mass is an average mass. The average mass is 80, but there is only two isotope mass, 79 and 81. So when you have 79 bromine is to 81 bromine, the average mass, the AR, is 80, exactly in between. And that is only possible because you have 50%, well, close to 50% of each, and that is exactly what it is. In the new syllabus, in the new 2023 syllabus that I'm teaching at the moment, so the students are expected to work out the relative atomic mass based on the percentage abundance. Okay, so 79 is the mass number, multiplied by 50%, well, 50, plus, I'm going to add it together. Now 81 times 50, I should probably use a different color so that it's clear. Again, I must emphasize that this one is in the new 2023 syllabus. So of course, if you're not doing that syllabus, things will be different for you. Okay, divided by the sum of the abundances. So it's 50 plus 50, which is 100%. The one on top, if you do it correctly into your calculator, I forgot where I put my calculator. So I get 8,000 on top there, so it's 100, and they give me 80, well, 80.00 or 80.0. In reality, it's not exactly 80.0. That's because I've assumed them to be roughly 50%. In reality, I think the final answer is supposed to be 79.9. When you use a more accurate periodic table, like the one available for A-level chemistry, 79.9. So that means you have just a bit more of this bromine 79 than bromine 81. But in hindsight, given that they're about 1-to-1, that is why that your average mass based on the percentage abundance or how much you have of each isotope in reality, they give you this average value that is somewhere in between 79 and 81, exactly in between. All right. So this kind of calculations is actually something new for the 2023 O-level syllabus, but it wasn't in the syllabus before this in any of the O-level or IGCSE exams prior to the 2023 exam series. So I wouldn't worry about it too much unless you are the 2023 exam takers onwards. All right. So on to the next question. So let me change the color. Which compound has molecules So they're talking about molecules. This one is ionic. In fact, you know that because it has got metal ions and it's got non-metal ions. This one is also ionic. It's got metal ion and it's got non-metal ions. So the bonding between metal and non-metal typically involve transfer of electrons. That's why you have giant ionic structure, because it's the interaction between the oppositely charged ions. So the fact that they tell you it's molecules, I can cross out C and D. And then they say covalent bond. So that should be even a giveaway that, you know, these are ionic. These are not covalent bond between the metal cation and the non-metal anion. So CH4 is one of the 10 to 11 simple covalent compounds that is stated very clearly in the syllabus, something you will have done as part of your lesson, as part of those lesson objective when you actually did the lesson. So you should be able to draw the display formula where you show them as lined. Each line represents one covalent bond. There is 2 electrons being shared, one from each of the atom, 2 covalent bonds. Here you got only 2 covalent bonds. Here you got 1, 2, 3, 4. Carbon form 4 covalent bond. So the correct answer there must be B. Question 6. What can be deduced about 2 gases that have the same relative molecular mass? The definition of relative molecular mass involves adding up all the sum of the relative atomic masses of all the atoms present in the molecule. Okay, so same boiling point that is to do with structure and bonding. So structure, bonding, and therefore what breaks. It's got nothing to do with, well, it's got some stuff to do with MR, but not really directly. Okay, kind of find the answer already. It's to do with rate of diffusion. You know that if you have gases that have the same molecular mass, they will diffuse at the same rate. They will travel the same distance in the same time. So same number of atoms in one molecule is not really correct. Let me think of a perfect example. I can't think on top of my head. Let me think. Nope, I can't think on top of my head. What am I thinking? Let me see. Enter is 14 times 2, which is 28. Same number of atoms in one molecule. CH3 is 15. Nope, I can't think on top of my head. I've seen something very similar, but you can definitely use example to come up with molecule that makes sense, but they have different number of atoms. So that's how I can tell B is definitely wrong. Not on top of my head right now. Okay, of my chem today. Same solubility in water at room temperature. That is not true, because you can have some gases that are more soluble than other. So just based on relative molecular mass, it's not going to affect the solubility directly. Question 7, that is to do with what I said before. That is to do with electron transfer, not electron sharing, because electron sharing is to do with covalent bond, and we are forming ionic bond between oppositely charged ions. They come from metals. Metal lose the electron and they form cation. And of course the electrons are being gained. The electrons are being gained by the non-metals. So they gain electrons and they will form anions. So these are all technical terms. Electrostatic force attraction between cations and anions, that is your ionic bond, not metallic bond, okay, ionic bond. Now to question 8, we have magnesium oxide. Again, metal, non-metal, this is going to be ionic. So actually it's Mg2 plus, O2 minus. And then the Al2O3 will be Al3 plus and O2 minus. The formula of which is Al2O3, because the compound itself has no charge. Plus 3 does not cancel out minus 2. So what you need is, you need to think about lowest common multiple, something from lower primary school. 2 does not divide 3, and then 3 is 1 and 1. So the LCM is 6. You want a total of 6 electrons being transferred from plus 3, so you need 2 of them. You want a total of 6 electrons being transferred from 2 minus, so you need 3 of them. That's why it's Al2O3. This question is not asking you which one has the higher melting point. In fact, they give you all the values. They are asking you over which temperature range will both of them conduct electricity. So these are both giant ionic compounds, giant ionic structure. They are both ionic compound. So giant ionic structure can conduct electricity only when molten or aqueous. However, if you look carefully, pure compound, they don't say mixture. When you are in water, in aqueous solution, there's a mixture. So this must be molten. We are looking at melting point and boiling point. We want both of them to be present. So if I have temperature, so if I have, let me put in some value, 2072. Let me use a different color. After that is 2852. Let me again use a different color. So these are not drawn to scale, obviously, but they are drawn from the lowest to the highest, such that they will make sense. If you look at from lowest to highest, so it's 3600. I should use the same color for the same compound. Okay, so 2852, and then I have 3600 over on the other side. Then the brown color I can use for this one. Okay, so if I say the brown color one is when I have liquid, what was I gonna say? When I have liquid MgO, because it's between the melting point, Al2O3 between 2072 and 2880. So what I do have is I do have liquid Al2O3, and then I could also have the pink color one where I have between here and here, where I will have liquid MgO. So in what temperature range, over what temperature range will both of them conduct electricity? So I can imagine here to here. So between here and here, both are liquids. Therefore, both of them will conduct electricity. If you exceed this one, this is already no longer liquid, it's already becoming gaseous. If you go lower than this is liquid, but this is a solid, so solid MgO does not conduct electricity because they are not free ions. So it's between 2852 and 2880. That's the best answer there. Okay. Question 9, I have used a bit of space down there, but anyway, which one conducts electricity? Remain chemically unchanged. So this is not electrolysis. Remain chemically unchanged. Let me think. Chemically unchanged. What does this question actually want from us? Conducts but remain chemically unchanged. Aluminium is a metal. So metal can conduct electricity and it still remain the metal. I think A is the answer here. Whereas for this and this, well, this thing is pure, not in water. So it is a simple molecule. It has a simple molecular structure. Does not conduct. You might think that it has H+, but no water. Okay, no H2O. No H+, therefore. Okay, so cannot conduct. So D is definitely out. Molten lead to bromide aqueous sodium chloride can conduct, but you need if you pass electricity, if you pass electric current through this will be electrolyzed. Okay, so they can conduct when you pass electricity through it, but they will be broken down into whatever is produced at the cathode and the anode, and therefore they will be chemically changed. All right, so A is the best answer there. Question 10, which statement most clearly indicates that diamond and graphite are forms of carbon? So this is basically about different forms of the same element. This is called allotropes. So they are of the same element. They are just different type of atoms of different forms of the same element. So both are crystalline solids. That is not necessarily true for graphite. So that is not true. Graphite is not crystalline at all. Complete combustion of equal masses of both solid. I've seen this question before. I know this is definitely the answer because I made a mistake previously. So both of them will give you this exact same equation. Carbon solid, I should probably write like this, where the stat symbol precedes, proceeds. It's after the element itself as a subscript. So balance equation, one carbon give you one carbon, two oxygen give you two oxygen there. So 1 mole reacts with 1 mole to give you 1 mole. Doesn't matter if it is graphite, doesn't matter if it is diamond, they both have the same balance equation for this combustion reaction, except that you'll be burning a very expensive carbon, where if you are using diamond and you still get carbon dioxide, which is a really cheap gas that we are breathing out, okay? So you don't want to burn your diamond, all right? So this is definitely the answer, because both of them follow the exact same equation, since they are different forms of the same element, which is carbon. So a lot of students, including myself actually, the first time I did this question, I actually chose option C. So this is a correct fact, but does not show. It does not show they are from the same element. It shows that they have different property, but it does not show that they are simply different forms of the same element. It's just, you know, conduct versus does not conduct. All right, so that's why C is not the best answer there. And of course, that's true that graphite can be converted to diamond. We can make artificial diamond. If you look at artificial diamond, they do it under very intense pressure, very high pressure. But those are synthetic diamonds, and those are not used in jewelry. They are usually used to make to make the diamond. They are used to cut the drilling tip or the drilling bits. They are used for mining purposes. All right. Question 11. So this is a hydrocarbon, so compound containing carbon and hydrogen atoms only. This is to do with gases reacting with O2, which is O2 gas. So gas reacting with gas, giving you another gas, which is all gases. They are all gases at room temperature and pressure at 25 degrees Celsius. So you got to think about X. So 1 of X reacts with oxygen to give you CO2. So this is going to be, let's say, CaHb plus H2O. So we don't know about this because this is a liquid anyway. All right, but we know that if you have 1 mole of these, then 1 time A number of carbon, this will be balanced by A. So the mole ratio of hydrocarbon to carbon dioxide must be 1:A. Okay, this is mole ratio from the balance equation. But remember that this is a gas, gas, and gas. Well, this is not always a gas, but it is a gas for each of these. All right, it is a gas for each of these, and as a result of it, since you have two carbon, that means you will get 2 CO2, 2 CO2 like that. You got 3 carbon, you will get 3 CO2. Got 3 carbon, you get 3 CO2. Now, how in the world can I balance this equation? So 1 cm cube of it give me 3 cm cube of CO2. Because these are mole ratio, and these are mole ratio of gases, and gases. As you know, mole of gas is equal to volume of gas divided by 24 dm cube per mole. Okay, so 1 mole of any gas occupies 24 dm cube at room temperature and pressure. That is actually given at the bottom of your periodic table. Of course, you should know it, but it's actually given for you at the bottom of your periodic table. 1 mole of any gas at room temperature and pressure occupies a volume of 24 dm cube. It's true for these as long as they are gases, it's true. And therefore, because this is a constant, okay, so the mole ratio of gases is equal to volume ratio of gases. So that is very important, because instead of just comparing mole ratio, I can see that 1 mole will give me a mole. So 1 cm cube, they tell me 1 cm cube of these give me 3 cm cube of CO2. So from there I can tell that volume ratio equal to mole ratio. So 1 of these give me 3 of these. I must have 3 carbon. That's how I can tell A and B are wrong, because only 2 carbon there. Okay, so it must be C or D, but how do I decide? Both of them give me 3 mole CO2. Here is why you also need the information on the oxygen as well. If you think about it, let's see, C3H4 plus O2 giving me 3 CO2 plus H2O. So if you have 4 hydrogen there, then you must have 2 water, because 2 times 2 is 4, so that balance out. We need to think about how to balance the oxygen there. 3 times 2 is 6, 2 times 1 is 2, altogether they are 8 because 6 plus 2 oxygen is 8 oxygen. This is a molecule. As you know, from structure and bonding, there are around 11 simple molecules in the syllabus that you're supposed to be able to draw and know the structure, like H2, Cl2, N2, etc., which include O2 for how oxygen exists as gas at room temperature and pressure. As mentioned, there are 6 oxygen plus 2 oxygen is 8 oxygen, so you need 4 of the molecule. So 1 is to 4 is to 3. This is mole ratio, but it's also to do with volume ratio of gases. Remember, these are all gases. I purposely don't want to talk about the H2O because that is not a gas, it's a liquid at room temperature and pressure. So 1 cm3 of these give me 3 cm3 of these. 1 cm3 of these will require 4 cm3 of these. I just coincidentally checked for this one. I knew that if I check for this one and it's not 4 there, the other one must be the answer. But I checked for this one and the answer is 4. So that means there's my answer there, being C. Question 12, what is the concentration? So you want concentration, 1 gram of sodium hydroxide in 250 cm3 of solution. So first of all, it's best if you work out the mole of sodium hydroxide, which given the mass is mass over mR, so 1.0 divided by big bracket, so 23 times 1 plus 16 times 1 plus 1 times 1. So pop that into your calculator. So it's 1 over 40, so that is 0.025 mole. Now I want the concentration. Concentration here is in mole per dm cube. So I have the mole and I have the volume. The volume is in 250 cm cube. Each of these is in dm cube. So I must convert the 250 into dm cube by multiplying by 10 to the minus 3. Some people don't like that, then you just do 250 over 1000. So 0.025 divided by 250 times 10 to the minus 3, I get 0.1. That is what my calculator show me. But the one that's given here is to 2 significant figure, 1 and 2. Look at the data, 1 and 2 sig fig. Well, this can be 2 sig fig or this can be 3 sig fig, but 2 sig fig seems to be reasonable and seems to be appropriate number of significant figure as given by the data in this question. Let me move this out a little bit. Question 13. So what do we have in question 13? This is electrolysis. We are using inert electrode. This is negative, so this is negative, this is positive, negative, positive. Negative electrode attracts positive charge cations. So this one attracts cations. Remember, cations are positive charge. Therefore, this is called cathode. This is called anode. Okay, so the negative charge attract positively charged cations. So this is again called cathode. This is again called anode. I can probably move this out a little bit there, and then I can move this out a little bit. Okay, cool. All right, now what do we know about electrolysis? We know that reduction happen at cathode, red cat, and we know that so a lot of these silly acronyms, how silly they are, I have no idea. I've always depended on these kind of silly things my entire life, and I turn out just fine. I know what is going on. I don't just memorize things like that, but I know the underlying chemistry. Reduction is gaining of electrons. Reduction happen at cathode, so regaining electrons happen at cathode. Cathode attracts cations. So what could be liquid Y there? So what's happening? So this is before, this is after. As you could see, these are volume. So the volume at the anode, the volume of gas at the anode, the volume of gas at the cathode is about double the height because there's about double the volume at the anode. So what is happening there? This is very common. H2 is to O2 is 2 is to 1. This is very common for electrolysis of water, because when water gets split, you get 2 H2 plus 1 O2 in that ratio. And what happened there is that is at the cathode and that is at the anode. So you're looking for H plus being discharged and OH minus being discharged. So you're looking for something where the cathode reaction is H plus 2 electrons giving you H2, and you're looking for these reactions that happen at the anode. OH minus will give you O2 plus H2O plus electrons, so there will be 2 of them, and there will be 4 of them, and 4 electrons. So these are very common Harvey questions which you should be able to write anytime, any day, and be able to balance correctly and from scratch, not just by memorizing, because memorizing doesn't help you when you forget one thing or when you make a mistake. Alright, so be able to check the atoms and the charges and know what the electrons on the left and on the right actually mean. Now let's have a look at the option. What could be the liquid wine? If you have aqueous copper 2 sulfate, you will have H plus OH minus from the aqueous solution. You have copper 2 plus and SO4 2 minus. Remember that copper is below hydrogen in the reactivity series, and we have inert electrodes, so we are not using copper electrode, we're using things like graphite, or we're using like platinum electrodes. So copper 2 plus will be preferentially discharged at the cathode. I do not need to check already the other one, but we know that OH minus will be the one preferentially discharged. This will give you O2 at the anode, because anions go to the anode. But this one will give you copper solid at the cathode. You will not get a gas, which is hydrogen here actually, okay? So aqueous copper 2 sulfate is definitely incorrect. Aqueous sodium chloride, so I can tell you H plus OH minus, Na plus Cl minus. So it is concentrated because I don't know why I put a cross there. That should have been for A. Concentrated means you favor the chloride over the OH minus, which means that this one will give you Cl2 at the anode, and therefore it does not give you the 2:1 ratio like for electrolysis of water. As a matter of fact, if you try to write this equation, you will see that NaCl, what do you get? NaCl plus water will give you H2, it will give you Cl2, it will also give you NaOH. And let me try to balance this equation now. 2 of that, so 2 of that, and I think that's balance. That is not balanced, so 2 of that, and yep, that's balanced now. So the gaseous ratio there is 1:1, whereas the volume shown here is 2:1, so it can't be that at all. Okay, so question could be very tricky, and they ask you about what's the ratio. Well, based on balance equation, you should be able to tell the ratio of the gases at the cathode and the ratio of the gases formed at the anode. For concentrated NaCl electrolysis would be 1:1. Now onto dilute sulfuric acid and ethanol. Very obvious C is the answer, because ethanol is a simple molecule, and I think this is one of the 11 or 12 covalent compounds that you're supposed to draw. Whether it's methanol, so this is methanol. I think the one in the syllabus under structure and bonding in topic 3, or whatever topic you call it, is basically this simple structure, simple covalent structure of methanol. It does not conduct electricity. Ethanol, you just add an extra CH2, so ethanol is just CH3 CH2OH. Again, it's also a simple molecule. Yes, I know this is methanol, I did not make a mistake. This is ethanol with 2 carbon, alright? But both of them are simple molecules, just like a lot of organic compounds, and therefore they do not conduct electricity at all. So you can't electrolyze, you can't break them into their respective elements by using electricity. But dilute sulfuric acid, you can, alright? Question 14, which substance when you add to water does not make a solution? So this is a negative kind of question. That is a good conductor of electricity. So you got to think about the ions. So Ba2 plus, nitrate is NO3 minus. In fact, you need BaNO3 twice as the formula. I hope you know how to balance the charges. You need 2 of these to balance out the 1 time plus 2 charge. So balancing one of these barium 2 plus, you need 2 of the nitrate. This is ionic. It's an ionic compound, so definitely it will dissolve in water. All nitrates are soluble in water, and it will, well, you have 3 ions in solution, so A cannot be the answer because it said does not. Okay, calcium chloride, Ca2 plus Cl minus, you actually have CaCl2. Let me go through the rest first. Pb2 plus NO3 minus. Again, very similar to barium nitrate. All nitrates are soluble. So regardless whether it's lead to nitrate or whatever nitrate, all nitrates are soluble in water, and therefore they'll give you 3 ions that can conduct electricity. Now this is zinc carbonate. This one will give you ZnCO3. So a lot of the carbonate of group 2, so you know group 2 carbonate. group 2 carbonate. Again, I am aware that zinc is not from group 2, but I'm just saying group 2 carbonate, M2 plus CO3 2 minus, is insoluble. Okay, so zinc is not group 2, but it is what we call, having the same charge is what we call divalent. So a lot of the divalent, meaning 2 plus charge, divalent cation, meaning 2 plus charge, they're going to behave like the group 2 carbonate. They are insoluble in water. So insoluble in water, despite being ionic, means that they're not going to give you the free ions that will conduct electricity very well. Okay, so calcium chloride is indeed soluble in water, so this is the best option compared to calcium chloride. Next one, we have a simple cell. So what do we know? We have zinc and we have copper. So zinc and copper. So if you have hydrogen as your reference point, and you know the more reactive metal will be the zinc, and then the less reactive metal will be the copper. So there is a difference in reactivity between copper and zinc, and having said that, you know that they will give you a potential difference, we call PD in physics. So this potential difference can be measured by a voltmeter. They give you the potential difference in volts. If you do O-level or IGCSE physics, you will know what a voltmeter is, you will know what potential difference is, you will know the unit in voltage, what it means. All right. So we have an electrolyte. Remember that we are generating electricity as a result of the potential difference. We are not doing electrolysis. This is a cell. Okay, so we are not doing electrolysis here. Since we are not doing, are we doing electrolysis? Let me think. We are not really doing electrolysis here. So zinc is the more reactive metal. The more reactive the metal, they like to lose electron. Oxidation is loss of electrons. The less reactive one, below hydrogen reactivity series, they like to gain electron. So this is gaining of electrons. Okay, so you like to gain electrons. So the electron is going to go from there to there. This one will gain electron. This one will lose electron. Okay, so they gain electrons. Electrons are negatively charged. If electrons are negatively charged, therefore the copper electrode is positively charged, therefore the zinc electrode is negatively charged, you lose the electrons. Okay, so the electrons flow towards something which is positively charged. Electrons travel through the solution. Yes, electron does travel through the solutions. Hang on, not really. No, electrons travel through the wire, isn't it? Okay, let's go through the options. Which statement about the process occurring when the cell in operation is correct? So you're looking for whatever is correct. So the zinc go to zinc 2 plus 2 electrons. The copper 2 plus 2 electrons go to copper. So having looked through the options, yeah, when you see what I've done here, so this is what happened at this positive electrode. The copper 2 plus gain electrons to give you more copper. So copper 2 plus ions are not formed in solution. Instead, you use the copper 2 plus to form copper. So that is wrong. That is copper 2 plus are reacted in the reaction. Electrons travel through the wire as a result of the potential difference. The electrolyte is just to complete the circuit. So as you could see, I've actually drawn the electrons flowing from the more reactive metal, which is more likely to lose electrons, towards the less reactive metal. They're more likely to gain electrons. Alright, so through the solution is actually incorrect. So the reaction, as I mentioned, here the zinc get oxidized and give you the zinc 2 plus, so that does occur, and in doing so the zinc does not increase in mass, the zinc decreases in mass as the zinc forms Zn2 plus that goes into the solution as part of the electrolyte. Question 16. So we have Haber process. Haber process is used manufacture of ammonia, so it's one of the few case studies that are very important. The other one being contact process that's used to make sulfuric acid. So high pressure, high enough temperature, and an iron catalyst. What change in conditions will give the reactants more energy? You are changing the energy distribution. So catalyst will never do that. changing pressure, changing temperature, they can affect collision frequency, but only temperature can change energy. Pressure, concentration does not change energy, because kinetic energy is to do with temperature. Okay, so temperature is actually defined as the average kinetic energy that a particle has. Okay, in A level it will make more sense, but even in O level, temperature is defined as a measure of the average kinetic energy. If you want more energy, you have to change temperature. Changing any other thing will not affect amount of energy you have. You can change pressure or concentration, and they will affect collision frequency, but they will not change your energy distribution. Only temperature will do that. And if you want more energy, you have to try and increase temperature to give you more kinetic energy. All right. Question 17, so this is to do with equilibrium. So you have dynamic equilibrium there. The forward reaction is exothermic, so forward reaction is exothermic. So based on what I'm about to explain here, if you are not very good with explaining equilibria, I advise you very strongly, I'll suggest you to actually check out my topical playlist. Check out the O-level or IGCSE topical playlist on chemical equilibria or chemical equilibrium, and find out more on how I will explain this kind of concepts, and make sure you could get it very well. Right? So you want to increase the amount of chlorine. Chlorine is on the right hand side, is a product, so you want more product. You want the equilibrium to favor to the right hand side. First of all, you can cross out catalysts. Catalysts affect rates. Okay, it only affects rates of reaction. It does not affect anything to do with equilibrium position. All right, when you add more HCl, then the concentration of HCl increases. What will the equilibrium do? The equilibrium tries to decrease. It tries to do the opposite. It tries to decrease concentration of HCl. How? It will react more HCl. When you react more HCl, the equilibrium will shift to the right hand side. When the equilibrium shifts to the right hand side, you will get more Cl2, and that's in fact what we're looking for here. Alright, what about the next one? So already gotten the answer, but I just want to show you that the rest are actually wrong options. Pressure. Pressure affects gases. Gases. So it's very important to focus on gases. These are gas, 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 and gas. So this is 4 molecule and 1 molecule on the left. So there are 5 gaseous molecules on the left hand side, and then versus there are 4, because 2 plus 2, both of them are gases, 4 gaseous molecules on the right hand side. So these are things they like to ask you in structure or theory paper. Yeah, okay. A lot of students tend to skip equilibrium questions, but they tend to be one of the easiest ones to score. You can have a look at some of my topical playlists, as I mentioned, on chemical equilibrium. So the more gaseous molecules you have, the higher is the pressure, because more molecules mean there will be more collision on the walls, because when you have more particles, they collide more with the wall, they give you more pressure. If you decrease the pressure of this equilibrium, the equilibrium will try to do the opposite, which is to try and increase the pressure. So it will try to shift to the side with more gaseous molecules. You have more gaseous molecules on the left, so equilibrium will try to shift to the left in order to try and increase the pressure, which is in response to your change. When you shift to the left, you will get lesser Cl2, and that's not what you want. You want to increase the amount of Cl2. Alright, in terms of temperature, I'll just explain this. The forward reaction is exothermic, that's why it's negative. Forward reaction is exothermic. Forward reaction releases heat energy. So it releases heat energy going forward. When you increase temperature, the forward reaction or the system will try to release less heat, because it wants to try and decrease the temperature. It will release less heat, and when you release less heat, it will shift to the left, it will shift backward, and therefore you get lesser Cl2, and that's why D is also the wrong answer. Question 18. So we got a lot of reactions involving ion compound. You're looking for redox reaction. The easiest thing is look for changes in oxidation number. So I know that oxidation number have been in and out of the O-level and IGCSE syllabus. In reality, oxidation number should never have been left out at all, which is why it's coming back. It's making a comeback for the 2023 syllabus specifically. I believe that a lot of teachers actually teach oxidation number because it's still a very useful trick to have. to identify redox reaction. Iron as an element is iron 0 as an element. This is iron 2 chloride. From the name itself is Cl minus. You need 2 of that Cl minus, and that is why this is iron 2 plus, which is why it's iron plus 2 for the oxidation state. For the second one, what do we have? This is iron 2 chloride again. That is iron plus 2. This is iron 3 chloride, because you have 3 of the Cl minus, so you must have 1 of the Fe3 plus. The oxidation state of ion is the charge on the ion, which is 3 plus, so the oxidation state is iron plus 3. What do we have here? Next one. This is iron 2 sulfate, so this is iron plus 2, because sulfate is SO4 2 minus, alright, and the overall compound has no charge, so it's Fe2 plus, which means it's Fe plus 2. This one here is iron as element, so it's iron 0. And last but not least, we have iron 2 sulfate again, iron plus 2. Here is iron 2 hydroxide. This is the dirty green PPT, as you would have known from your paper 3 or your paper 4, both to do with practical anyway, but of course it's also in your theory paper under qualitative analysis. Iron 2 hydroxide is dirty green, insoluble in excess, and an OH, alright? So it's iron 2 hydroxide, so it's iron plus 2, 1 of the iron 2 plus, and 2 of the OH minus. So look for changes in oxidation number. First one is definitely yes, from 0 to plus 2. Second one, plus 2 to plus 3, there's a change. We don't really need to worry about increase or decrease, because if it is redox reaction, there is a change. Redox means reduction and oxidation. If you see an increase, something must decrease. This is hydrogen plus 1 go to hydrogen 0. There's your reduction. This is your oxidation. Iron plus 2 going to iron plus 3. There is your oxidation, increase in oxidation number. The chlorine is 0, goes to minus 1. There's your reduction there. Okay. Plus 2 going to 0. There is your reduction. That's because the Mg goes from 0 to plus 2. There's your oxidation. So this is redox as well. And last but not least, this is iron 2 sulfate, iron plus 2. This is iron plus 2. So this is not a redox. So 1, 2, and 3 only. So there are 3 of them which are redox reaction. Question 19, what is the use of sulfuric acid? Sulfuric acid, you cannot believe how many people, how many GCSE, IGCSE, or O-level students don't even know the formula of a common acid. This is actually formed as part of contact process. You can never get formula of this wrong, just like you can never get the formula of other ions incorrect, okay? H2SO4 used as a bleach, not really. You use Cl2, you use SO2. This is used for bleaching wood pulp, if I'm not mistaken, but Cl2 is commonly used. I'll probably stick with Cl2 actually. So we use bleach, this as a bleaching agent. Manufacture ammonia, so that is not true. You use it to manufacture fertilizers, yes, such as ammonium sulfate, NH4 plus, SO4 2 minus. For ammonia, you need ion catalyst, you need N2 reactant, H2 reactants. In the manufacture of sulfur trioxide, not really. That one you need SO2 plus O2, famous equilibrium, contact process, main-mate, alright? So 2:1:2, there's your balance equation there, alright? So there's only one answer there, which is to use to make fertilizer, to manufacture fertilizers. Question 20, so we have some solubility here of metal Q in cold water. So the carbonate itself is insoluble, so I can cross out sodium because all sodium salts are soluble in water, including Na2CO3. Na2CO3 is sodium carbonate, Na plus CO3 2 minus, so it's Na2CO3. The chloride is soluble, so all chloride is soluble except for lead 2 chloride. So PbCl2 is a white precipitate. Silver chloride is also white precipitate. Both of these chloride are insoluble in water. Now onto the sulfate, barium sulfate versus magnesium sulfate. If you know your QA, which is from your paper 3, they like to ask you in alternative to practical in paper 4, of course, plus paper 1 and paper 2, in fact, all of theory paper as well as practical paper. This is a classic white PPT. because this is the test for sulfate, test for SO4 2-. So very clearly it's barium and it's not magnesium sulfate there. Next one, we have metal M. So this chloride dissolved in cold water. The oxide dissolved in both strong acid and strong alkali. So therefore, we're looking for amphoteric oxide. We're looking for amphoteric oxide and the chloride dissolved in cold water. Amphoteric oxide, I'm very clear that this is zinc or aluminium that will form amphoteric. Why did I say acid? What I meant is amphoteric oxide. So example, zinc oxide and Al2O3. So this is a factual question here. All right. So sodium oxide, Na2O. If we have lead oxide, PbO, PbO2. So this is lead 2 oxide. This is lead 4 oxide. Iron 2 oxide. Iron 3 oxide. Okay, so a lot of these oxides, they are metal oxides, and despite zinc being a metal oxide, zinc oxide is also amphoteric. So a lot of these, the rest of them, they are all basic oxide. Okay, so these are all basic oxide, not amphoteric. Moreover, you can cross out lead definitely, because lead chloride is insoluble in water. Okay, insoluble in water means does not dissolve in water, so you can cross out lead. 22, so very clearly we're looking for something which is transition metal. So transition metal can have many oxidation state. Variable means many, more than one. So iron is one thing there, so iron plus 2, iron plus 3. You can use iron as a catalyst in Haber process and you form colored compounds. So iron 2 hydroxide, for example, iron 2 hydroxide is a dirty green PPT. Iron 3 hydroxide is a reddish brown PPT. So these are colored compounds just of iron, and there are many other colored compounds transition metal. You can check out some of my experimental tutorial series in another playlist, and you can see some of these QA results and some other useful practical techniques, not only for practical but also for alternative to practical as well. So next question 23. So if you ask on this, it say an atom. So you want an atom, so meaning to say number of protons equal to number of electrons, because an atom is uncharged, have the same electronic configuration as strontium ion. Strontium is from group 2, so it's a group 2 ion. So group 2, not the, has to use a Roman numeral because this is O level or IGCSE. So strontium Sr, so it's group 2, so when they form ion, they'll have this fully filled outer shell, noble gas configuration, Sr2+, there's going to be krypton electronic configuration, straightforward there. 24, boiling points of gaseous elements increases as the size of the atom increases. Which one has the highest boiling point? Highest boiling point would mean biggest size based on the information that they have told you. If you read that, as the size of atom increase, the boiling point increases. So this is noble gases. So group 8, helium, neon, argon, krypton, xenon. So the size of the atom increases as you have more and more shells being filled in across each period. So the one furthest down, we're looking at krypton. Out of the 4, krypton is the one furthest down. If you have xenon will be the answer there as well. 25, you have 2 metals and their oxides. So X could be copper because its oxide is, well, when you have copper oxide, CuO, so this is copper 2 oxide, copper 2 plus, O2 minus. Copper 2 oxide is basic. And then this is amphoteric. So when we're looking at amphoteric oxide earlier on, we can have zinc oxide or Al2O3. There was an earlier question about amphoteric oxide. It reacts with both acid and bases. If I find that question, has an oxide which dissolves in both strong acid and strong alkali. We're looking for amphoteric oxide, of which there's zinc oxide and Al2O3 based on your syllabus. Okay. So there's no zinc there, there's just aluminium for option 2 there, so it's to be aluminium. And then the first one, copper 2 oxide is basic, so it's B there. 26, how do you convert copper 2 oxide to copper? So in the reactivity series. So if you have reactivity series, you have more reactive metal, like to lose electrons on top, potassium, sodium, blah 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 blah. Then you have hydrogen, copper, silver, gold. So this is the less reactive metal. And if you have copper, and copper is below hydrogen in the reactivity series, so you could use hydrogen gas. Hydrogen gas can reduce copper 2 to copper, and itself will form H2O. So this one is hydrogen 0, this one is hydrogen plus 1, so that is oxidation. So it can itself is being oxidized, but it reduces the copper 2 plus, which is copper plus 2 in copper 2 oxide to give you copper 0. So this is reduction. So overall, this is a redox reaction. We could use molecular hydrogen, not nitrogen. Nitrogen is a fairly reactive gas. It's already oxide, so there's no point of reacting with oxygen. It's no good doing it with carbon dioxide either. Hydrogen is the best reducing, well, it's not the best reducing agent, but it's suitable to reduce copper 2 to copper 0. 27, so you have aluminium and copper used to make coins, but iron is not. So what's the reason for it? Well, iron is iron above aluminium and copper? Let's have a look. So I have the series here, but it's not that complete. So if I try and complete it right now, so is it potassium, sodium, calcium, magnesium, aluminium, zinc, what else? Iron, lead, and then etc, etc, etc. So we know that iron is there, iron is below aluminium, iron is above copper, so above both is incorrect. Iron is below aluminium, so A is already wrong. Iron is more expensive to manufacture than aluminium or copper. That is perhaps correct when you think about blast furnace. So you need to use blast furnace, you need to use carbon monoxide, CO as a reducing agent, CO as reducing agent to reduce the iron 3 oxide, the iron 3 plus, all the way down to iron. Iron can react with water. That is indeed true. If you have water, if you have salt, if you have moisture, so water or moisture, if you have salt, what's the other one? Oxygen or the air. So you have quite a lot of oxygen in the air, you can get rusting. Okay, so that is the best answer there. Question 28. So electrolysis of molten, so this is liquid aluminium oxide. What are the three reactions? These are the three reactions that take place. Which one take place at the positive electrode? So positive electrode will attract negatively charged ions. It will attract anion, which are negatively charged. Therefore, this is anode. Okay, so what happened at anode? We know reduction happened at cathode because of this silly acronym, red cat, and we have oil rig. So we have reduction is gain of electrons. Reduction happens at cathode. So this is loss of electron. This is oxidation. This is gain of electron. It is a reduction. So not this, because you want something at anode. So it has to be 2. But then as you produce the oxygen can also react with the graphite anode. Okay, so this thing, graphite anode, is the electrode for the anode. Carbon can react with the oxygen produced to give you carbon dioxide as well. So that's why you have to replace the anode from time to time. 29, we're back at this blast furnace in order to get the iron Fe from its ore hematite. This is iron Fe2O3. Okay, so which one is removed from the bottom? Okay, oops, I don't want that. So you want to get pure liquid iron coming out at the bottom. So you do have liquid iron at the bottom. They will come out as molten liquid, and then you can pour them into whatever malt you have, whatever malt that can shape the whatever shape that you want upon cooling. So definitely you do have that, and you do have this slag as well. So slag is actually the result of these reactions. If you add calcium oxide, if you have silicon dioxide present in the as part of the ore, okay, so you get CaSiO3. This is the salt, this is the acidic oxide, and this is the basic oxide. So it's a neutralization reaction. And so basically this is removed at the bottom of the blast furnace as well. As a result of this reaction, they try to remove this impurity from your hematite ore. So you do get that and that. Limestone will not survive because limestone will decompose to give you CaO and CO2 gas. The CO2 gas will escape, but the CaO is the one that react with the SiO2 impurity. Alright, so this coke is just carbon. The carbon is your source of reducing agent, which of course you get converted to CO, and CO is carbon monoxide, and you can use carbon monoxide to reduce the iron trioxide all the way to iron metal. So it's just 2 and 4 there. Number 30, you have an alloy. Alloy is a mixture, so you're just mixing two metals together, and you have copper and zinc. You have dilute hydrochloric acid. First of all, when you filter it, you get unreacted copper solid, so no copper 2 plus, therefore no blue solution. So your solution will be colorless, but your residue will be red, brown, or sometimes they call it pink, brown solid, which is copper solid. Now this is basically about reactivity series. If you're above hydrogen in a reactivity series, such as zinc is above hydrogen in reactivity series, it can react with dilute acid. Copper is below hydrogen in reactivity series. Copper does not react with dilute acid, but copper can react with concentrated acid. Right? So you can catch my topical, not really topical, but experimental tutorial video series. There's one video on the chemistry of copper. The first reaction I did there was a copper plus concentrated nitric acid. It's a fascinating reactions, but that was with concentrated acid. So copper can react with concentrated acid, but not with dilute acid. Okay. 31, you want to get ammonia from ammonium salt on heating. So you know this as a test for ammonium as part of your QA. Usually asked in paper 3, always asked in paper 4, always asked very popular in your other theory papers, such as this MCQ, as well as your structured theory paper. They can ask you to write equation, ammonium plus hydroxide, whether it's sodium hydroxide or calcium hydroxide. You heat it, you will release ammonia. Okay, so what happened then is, this is the base, it accepts the H plus from NH4 plus, so this is acting as an acid. It loses the H plus, then when it loses the H plus to the OH minus, you will also form water. This is the ionic equation, and it has to be balanced for every single ammonium plus hydroxide reaction. It always comes down to this ionic equation. So you're looking for anything that has hydroxide that can do the job, because any hydroxide will be able to abstract or accept the H plus from the ammonium salt. This is a common feature. They come out again and again. They ask you to test for NH3 with a red litmus paper. They will turn blue. You can watch one of my experimental video tutorial that is on ammonium salt, so do check that out. 32, aqueous solution of compound X reacts with zinc chloride to give you quite a lot of questions on qualitative analysis. Anyway, so reacts with aqueous zinc chloride. You want to form white precipitate, but dissolve in excess of X. Okay. So first of all, we know that zinc, if you have lead, if this is lead 2 chloride, if PbCl2 or AgCl, these are white PPT. So these are the tests for chloride, by the way. Okay, insoluble in excess. So it can't be this, alright? So cannot be, therefore cannot be. So what can it be? Ammonium sulfate form a white precipitate which is insoluble. So this white precipitate has to be a barium sulfate because all ammonium salts are soluble in water. This is part of your syllabus, which stated that you should know the solubility of rules. Are soluble in water. So all of ammonium salts are soluble in water, so this precipitate must come from the anion, which is the sulfate. So there's a test for barium sulfate. So it has to be, looks like it has to be, yeah, it has to be something that contains the sulfate. So we are looking for this barium 2 plus, I think. Or could it be silver? It cannot be silver because silver chloride is insoluble in excess silver nitrate, so it cannot be that. Can it be ammonia? Can it be ammonia? Let me think. If it is barium sulfate, then I'll get barium sulfate. Sorry, this is not ammonium. This is aluminium. I don't know why I wrote down ammonium. Okay, so it has, so that thing there, the white precipitate there, is barium sulfate. But if we look for barium, then you have chloride. Aluminium chloride is not a white precipitate. Aluminium chloride is not a white precipitate, so it cannot be barium. Therefore, not Ba2 plus. For the reason I just said, it cannot be this because what was I saying? Could it be that? Let me think. X. It cannot be because of the first one. The zinc chloride and barium chloride has no reaction. So barium chloride and zinc chloride, no reaction. But if you read the question above, they do have a reaction. They form a white precipitate. So it comes down to two classic things, which is test for cation. So we are really just testing for cations here, either using ammonia or sodium hydroxide. So first of all, what will we get? We will get zinc hydroxide. We will get aluminium hydroxide. So both of these are white precipitate, but these dissolve when X is in excess. So in excess hydroxide, this will dissolve, and this will also dissolve. Oh, hang on. Will this dissolve? Hang on. So yeah, both of them will dissolve in excess hydroxide. So zinc and aluminium both dissolve, both PPT dissolve in excess NaOH. So if both PPT dissolve in excess NaOH, you are not, excess sodium hydroxide. So you're not going to be able to tell from just this test alone. So we have to look at the second one. So the aluminium hydroxide does not dissolve when ammonia is in excess, but zinc hydroxide dissolve when ammonia is in excess. And this is insoluble in excess ammonia. Therefore, we are looking for this thing which is insoluble in excess of that. So 32 has to be option A as the answer. 33, CFC compounds, chlorofluorocarbon is contain carbon fluorine, contain carbon chlorine, it's also got alkane. So which element causes a depletion of ozone? So we are breaking the weak CCl bond. So the CCl bond is the longest, because when you think about it, hydrogen has just got the first shell, fluorine has got 2 shells, chlorine has got 3 shells. So it's the longest covalent bond. And it's the longest covalent bond because chlorine is bigger than fluorine, than hydrogen, more shells. Okay, more shells occupied. And if it is the longest covalent bond, then it's the weakest covalent bond. If it is the weakest covalent bond, it's going to be the one that you like to break the most, and you can get something called free radicals, something that will make more sense when you go to A-level chemistry. 34, most likely to react with limestone. So this is calcium carbonate. You're looking for something which is acidic. So this is acidic oxide. This is basic. This is a neutral oxide. And of course, methane is also, it's not an oxide. Oops, I don't know why I circled that. So we're looking for acidic oxide, which is sulfur dioxide there, that can form acid rain and destroy this calcium carbonate by reacting with it. 35. So I hope you can see this is the ester. So this is the ester linkage. It looks a bit weird. Usually it's like this. But no matter how weird it is, you get a carbon-oxygen double bond. Next to it is a carbon-oxygen single bond. So when you want to break the ester, this is the linkage that you break. So you hydrolyze here. So when you hydrolyze there, that bit gives you the alcohol, which is OH, CH2, CH2, CH3. This is a 3-carbon alcohol. So this is going to be 3-carbon alcohol, 3-carbon alcohol. This is wrong because this is 4-carbon alcohol. Now let's have a look at the carboxylic acid. The carboxylic acid is the one that has the C double bond O. So it's CH3, CH2, CH2, CO, OH. That is essentially what you lose. That is essentially what you lose. This is essentially what you lose, because going to form the ester, you're going to do condensation. Okay, so you learn condensation, polymerization to form polyester. So when these two things come together to form ester, it's not polymerization, it's just called condensation. This loses a OH, this loses a H, this and this form a bond, which is the bond that we're breaking here. So now you have 1, 2, 3, 4. You have a 4-carbon carboxylic acid. So this has to be butanoic acid, which is 4-carbon carboxylic acid there. So question 36, you have fermentation. So you start out from glucose, or what you call sugar, C6H12O6, and then they'll go to C2H5OH, which is basically the formula for ethanol. So you can also write CH3CH2OH if you want to, and they will give you CO2. So we need to balance the equations. So let's see, 6 carbon, so there's 2 of these and 2 of these, and that should take care of itself. 6 hydrogen altogether, 5 plus 1 is 6, 6 times 2 is 12, 2 oxygen, 4 oxygen, 2 times 2 is 4, plus 2 oxygen give you 6 oxygen, 4 carbon plus 2 carbon give you 6 carbon. So you're fermenting a carbohydrate and not hydrocarbon, because hydrocarbon contains only carbon and hydrogen. This one contains oxygen as well. You evolve carbon dioxide, not carbon monoxide. So answer must be A there. 37. So you're looking for the CO group being present in the linkage. When you have ester, you have C double bond O. When you have amide, you have C double bond O and H. They are looking specifically for something called the C double bond O. So we know this name, nylon. So there is what we associate as polyamide, and then this is an addition polymer. So polyethylene is an addition polymer. It's non-biodegradable, and then terylene is the one used for making textiles. So there is your polyester. So polyethylene is just, it came from ethene, which has a carbon-carbon double bond, but then when you form polymer, you lose the carbon-carbon double bond and you extend on both ends, and carbon form 4 bonds, 1, 2, 3, 4, carbon form 4 bond, 1, 2, 3, 4, part of the polymeric chain. This one has no C double bond O at all. So it has to be nylon and terylene only. So they're not looking for amide or ester, they're looking for C double bond O group, which are present in both ester and amide. 38, if we polymerize butene, okay, so my suggestion is for you to draw and see for yourself. Instead of looking at the answer, instead of looking at the options, draw and see for yourself. So this CH2, CH3. You should really be treating this whole group as CH2, CH3 like that. It could be an R group, does not matter. Your polymerization happens here on the carbon-carbon double bond. Focus on 1 and 2. So this is your 1 and 2. So what happened then is you lose the carbon-carbon double bond, and now you have 2 open chain. Okay, then put in what is that carbon 1, hydrogen, hydrogen. What is that carbon 2, hydrogen, and then CH2, CH3. Now you have lost the carbon-carbon double bond. You still have a carbon forming 1, 2, 3, 4 bond, 1, 2, 3, 4 covalent bond. They are both open-ended now, so it's now part of the polymeric chain. No more carbon-carbon double bond. This is your R group. Do not change anything on the R group. They are just what you say a side chain. They are just extension of the side chain. You don't do any polymerization there. You do your polymerization. This is called addition polymerization because you are adding across the carbon-carbon double bond. So what do we have? This is just carbon 2 and carbon 1. This is actually correct already, and this is wrong because where is your R group? This is wrong because CH3 and CH3. This is CH2 CH3. Your R group side chain is CH2 CH3. Okay, so D is wrong, and here this is wrong as well because of the same reason. Okay, so A is correct, and they try to think of it as the other way around because you could also have CCH and you could have CH2 CH3 like that, and you could have H like this. Of course, that is exactly the same as CH2 CH3 H and H. So what I've done is I've shown you this is the same as this is the same as this. So this and this, there are 3 of the same compound. They are exactly the same. They are same compound. They are not isomer or anything. They are exactly the same compound because you can rotate, flip the whole molecule like this, whereas from here to here you flip this molecule like that, and then this will go to this side. Okay, so not a big deal at all. You should be able to understand and see that they're the same thing. 39. So glucose is a simple sugar, so that's the monomer, and glycine is an amino acid. So carbohydrate is made out of simple sugar, so that is correct. Carbohydrate is made out of simple sugar. Hydrolysis simply break down the big molecule into the smaller units. Carbohydrate does not give you amino acid. This is simple sugar. This is amino acids. So amino acids are the building blocks of protein. Protein does not give you the glucose upon hydrolysis, so only 1 and 4 are correct. So this is a factual question. Question 48 is the last question in this multiple choice paper. What do we have here? Highest boiling point to lowest boiling point. So lowest boiling point means most volatile. Most volatile means it boils off easily. So this must be the shortest chain. This must be the smallest molecule. Okay. What else do we know? Highest boiling point. So this must be the longest chain. And this must be the largest molecule. Okay, so you want the correct order of their boiling point. So this comes down to whether you know your fractional distillation. So a lot of these options here, they are not the common one. So not like bitumen, which are easy to identify, those kind of thing. But we should be able to work through these options here.